My name is David Sisson. I'm a senior engineer at Block Science, and I'm going to review some progress in information technology, and I'm going to make some predictions based on that as to what may happen next. And hopefully this will be somewhat informative and maybe even fun. So basically, the agenda I'm going to go through is I'm going to describe IT in three phases. I'm going to start out with a computer, specifically personal computers. I'm going to go into the network of computers, the internet of Al Gore fame. And lastly, I'm going to talk about a network computer. And then, based on those three phases, I'm going to make a prediction as to what comes next. And if you can't guess, it's a network of network computers. So, and then I'm going to finish up my talk about talking why a network of network computers might be worthwhile, and how it's not just a recognition of some trivial pattern in a sequence of words or an exercise of how many times I can fit the words computer and network on a single slide. So to start, we've got three historical phases, starting off with a computer. So specifically, we're talking about a personal computer of say, 1980 ilk. So what is that kind of a computer? Well, at first approximation, a computer is hardware with the ability to process data by following instructions. So there's memory and there's to store both those instructions, the programs, and the data state for those instructions to operate on. And then there's a processor to execute those instructions. And by doing that, we're mutating the state of the machine deterministically. So basically, we've built ourselves a little state machine. And add on to that, as many of us have learned firsthand, if the user experience of interacting directly with a box of memory and processor is pretty bad. So we layer an operating system on top of that to improve that user experience. So what is this computer good for? It's to help an individual creating and manipulating content. So static content like text or rich text files, static pictures, motion pictures. Or we can get into dynamic content like applications, text editors, spreadsheets, compilers, that sort of thing. So basically, a personal computer is there to improve the efficiency of a single person. To give a little bit of the flavor of the times, I've got a quote from Steve Jobs where he compares computers to bicycles. And the gist of it is that, he read a report where condors were measured to have a more efficient locomotion than people, largely because condors can soar, so they're just sort of holding their wings out while they travel from place to place. However, if you take a person and pair that person with a bit of technology, a bicycle, that the locomotor efficiency of that person increased about 5-fold times. So with that increase, the human is now more efficient than the condor. In fact, the human is probably one of the more efficient locomotors measured in this study. And this impressed Jobs enough that he based a marketing campaign for the first Macintoshes on it. Now, I could have chosen a quote from, say, Bill Gates to illustrate the times, but somehow DOS ain't done till Lotus won't run didn't quite fit the spirit of this talk, so we'll go with this one. So the next phase I want to talk about is the network of computers. So what is a network of computers? Basically, it's computers connected by standard hardware and software. It gives the connected computers the ability to share data between themselves. So what is a network of computers good for? Well, if we go back to what I just said it was, obviously it helps a local computer to communicate directly with computers in other locales. And in doing so, we have a network of computer provides infrastructure for things like the World Wide Web. And we've got, Tim Berners-Lee developed that through composition in about 1989 of standards that he developed. HTML, URLs, and HTTP. And from hyperlinked static web pages, we get to dynamic content, eventually culminating in sort of the now ubiquitous REST API protocols that let one computer send post requests to another to run a job and then send GET requests to retrieve the results of that job. And if we drill down a bit and look to see what this standardized network looks like, the architecture is shown here. Side by side, there's a comparison between sort of the conceptual networking model we call the Open Systems Interconnection Model, OSI model, and then the TCP/IP model, the packet switching model that the internet actually uses. OSI model was developed about 1984 by, oddly enough, the ISO. And the TCP/IP packet switching network was developed during the 70s and incorporated into a precursor of the internet, ARPANET, in about 1983. So one interesting thing here is, not surprisingly, the physical development of a concept. Well, let's see, the physical TCP/IP predates the conceptual OSI, and that it helps to illustrate that sort of bottom-up development of a concept can help keep it grounded in reality. So we'll keep that in mind. And a quote for the Times, again, Tim Berners-Lee describing sort of what he had wrought. And to give some of the key aspects of this network of computers we call the internet, at a first approximation, and I'm going to say a first approximation a lot of times because this talk is not getting into too much detail. At first approximation, conversations are between two computers. A given conversation is generally the case where one computer is a client and the other computer is a server. So one computer is doing the requesting and the other is serving some HTML or running a job and returning results. And the mode of the conversation is stateless, meaning that the protocol is only interested in the here and now. What came before the request, what might happen after the request, is the responsibility of the clients and servers, not the protocol. So we go to the third historical phase, which takes us pretty much to today. I'm going to talk a little bit about a network computer. And what do I mean by that? Well, it turns out that by swapping the client-server OSI layer 7 protocols, such as HTTP, for peer-to-peer protocols, such as libp2p, you can develop decentralized network consensus protocols. And the individual computers, not clients in this case, not servers in this case, but peers, can participate in maintaining the state of the network. And it's a rather small step from there to include rules to deterministically mutate that state. And so we've come full circle, and now we've got sort of a second-order state machine, a network that is a computer. And one thing to note here is that we're starting to get into fractal territory when we start talking about things like this. So just like we experienced with first-order computers, the user experience of interacting directly with a box containing processing and memory is still pretty poor. So please layer in an operating system over the state machine to improve that. And I think we've heard talks here, Bacalhau and the projects presented here at this conference have largely focused on improving user experience of this machine. So good progress is being made, but there's still a ways to go, still work that needs to be done. Now, what is a network computer good for? A network computer is to an organization, I would say, what a personal computer is to an individual. It can assist an organization, a group of individuals aligned in some way, here by their shared peer-to-peer networking consensus protocol, with creating and manipulating content. So for example, a decentralized ledger of accounts could be that content, or decentralized applications. And such content can externalize value that's been produced by the organization, or the organization can use them internally for organizational and governance purposes. And we come up with things like DAOs. So these sorts of things become possible with this network computer. So I tried to come up with a quote for the flavor of these times, and these times being these times, I described my presentation to ChatGPT and asked it for a quote. I was hoping for a list of things that some famous people had said, but like a good algorithm, it took me literally. And so this is ChatGPT's quote. And I also asked it how it would like me to attribute itself, and that is the attribute tag that ChatGPT prefers. So basically from this, we can all, the take-home message is that ChatGPT has drunk the Kool-Aid. So some key aspects of this network computer are, it's composed of groups of peers running standard protocols for communicating between peers. The purpose of this protocol is to achieve consensus about the state of this computer across its peer nodes. The protocol contains rules that define how state can be mutated, and in some of these networks, the state mutation rules contain or allow for the creation of new rules. So the network computers are programmable or can be programmable. So the mode of conversation, and one important point is the mode of conversation mediated by these protocols is then all about state. Or to put it another way, the protocol exists to develop an internal representation, consensus about what has happened from the point of view of some organization. So that's history. Now we go to the prediction. And like most next step predictions, this one's pretty obvious. So, as I previewed in the agenda slide, I think that the next step is a network of network computers. And so here I'll start out with a quote, and I swear this quote fits. I'm not just sucking up. But I'll modify it. I'll say, however, rather than describing the first order internet as broken, I think it's more accurate to say it's just not the right tool for the job we want to do. So here's a sort of architectural diagram of what might happen next. So what is this network of network computers? It is individual network computers now, joined by standard software. We've left the realm of hardware behind. That allow one network computer to share its state, its internal representations, with other network computers. And what is a network of network computers good for? Well, you can think of one thing would be something along the lines of sensor fusion. So each network computer's internal representations could gain accuracy or generality through some kind of mechanism like decentralized federated machine learning. So this is the modern day version of the blind man and the elephant story, where each observer only perceives a part of the whole, and the whole only becomes apparent and understood by combining the parts. And for another, internal representations look a lot like concepts. And concepts and relations between them have a lot in common with what we call knowledge. So we may be moving from sort of data and information flowing through first-order network circuits, just something that begins to approach knowledge, or at least concepts, flowing through the second-order network. And, could this lead to better understanding? Maybe. Could it produce wiser decisions? I don't know, but maybe. Now keep in mind that each computer network would still have its own unique internal representations. It would take a second-order network computer to arrive at a cross-network consensus reputation. But we've just gotten to OSIB, so it's a pretty big unknown right now. And I don't think it's time to start worrying about the architecture of a third-order state machines. So the network of network computers, so to speak. So I've managed to fit a few more networks and computers into this talk. So what can we tell about, or what can we predict about what this network architecture might look like? Something that could do the job we're asking it to do. As I said, we're in fractal territory, so we can look back. We can look at where we've come from, the internet we have today. And we have this nicely layered out conceptual OCI model. And it's a reasonable place to start. So let's make the assumption that this conceptual, this second order network will have the same kind of layered architecture. But might the physical implementation then look like? And this is certainly good, fertile ground for research. But there's some ideas kicking around. For instance, something like interplanetary consensus protocol. My understanding of that is the primary design goal is horizontal scaling of something like the Filecoin network. But it also has properties that are similar to a local area network, which is that bottom network access layer that we see on in the TCP/IP model. So could something like that provide the basis for the internet the next level internet we're looking for? And then what sort of protocols would be needed at the network layer, at the transport layer? How do we get wide area networks? And certainly, what does the application layer look like? Well, one thing I'd like to suggest here is that the function of this second order network, so what kind of applications may run, is to communicate something akin to knowledge, concepts, and relations between concepts, derived from shared state, which is in turn derived from data and information communicated on the first order network. And now a word from my sponsor. So at Block Science, we have two projects that are relevant to this second order network. One is CATS, Content Addressable Transformers. The goal of CATS is a unified data product collaboration framework to establish a scalable and decentralized data mesh of verifiable computing workloads with data provenance. So no small task. Joshua Giudesti, he's here today. He's the primary research engineer on CATS. And the other project is KOI, which is Knowledge Organization Infrastructure. And KOI right now is a fairly basic indexer of Block Science's documents and communications from a wide variety of platforms and sources. But we're using it to research ways to have KOI play a role in identifying similar items, similar communications, published to different media through different channels. And we look at this as sort of a rudimentary form of concept mapping. So we're researching how to communicate concepts in this second order network. So there's some parallels between the proposed architecture that I've shown here and some systems that we may be familiar with. So take the other massively parallel computer we all know about as an example. I happen to have a cerebellum. It has kind of a homogeneous modular architecture if you look at the cells that make it up, the neurons. If you look at the circuitry, it's basically all feed-forward processing. It kind of looks like stateless protocols. And it participates basically in coordination. It's for coordination of complex behaviors, making complex things look easy. And I think that kind of maps nicely to what the first order network is actually good at. Now if we take a look at the cerebellum, or the cerebrum, that top multicolored thing, It is heterogeneous. It has an area architecture, unique organization, sort of like unique organizational state machines. So for instance, that blue blob on the black back is the occipital lobe, and it processes vision. Touch and spatial awareness happen and are processed in the parietal lobe. Audition and memory, temporal lobe, voluntary movement, and cognition are frontal lobe. I talked about sensor fusion, so in the frontal lobe, those other sensory modalities are fused into sort of a internal representation of the external world. So also in the cerebrum, we have circuitry that's capable of both feedback and feed-forward processing. So with that the addition to feedback, we can have a sort of stationary signals being produced, and we can become stateful. So this maps nicely to what I've mentioned in terms of the second order network. So, you know, are we moving in this direction, in this internet that we're building? Moving away from a biological metaphor to a business metaphor, there's the viable systems model framework developed by Stafford Beers in the 70s. You may not be familiar with it, so I've blown out a description of it here. Basically, the organization is divided up into M, management, O, operations, and it interacts with an E, environment. This is Stafford Beers' diagram. If it were to be redrawn today, we might take the circle around the environment and extend it to include the organization as well, because it's thought that no organization is actually outside of the environment that it operates in. And the VSM model is divided up into 5 systems. System 1 represents operations. And I don't know if you can see in this diagram, but basically it's a fractal, a recursive model. So the operations are themselves a viable system. System 2 represents information channels that flow from primary activities in System 1 to the management systems. System 3 establishes the rules, rights, and responsibilities of System 1, make sure it has the resources it needs to do what it needs to do, and provides an interface up to Systems 4 and 5. System 4 is responsible for looking outwards into the environment, making sure that the organization sort of knows what it needs to know to adapt to remain viable as the environment changes. And System 5 is responsible for policy decisions within the organization as a whole, balancing demands from different parts of the organization and steering the organization. So if we take that model and we put it against sort of what I've been talking about, it fits right nicely in where the brain used to be, and there's really no surprise to that because the VSM model itself is influenced by our understanding of how the human brain works, and Beer's first book about the model was titled The Brain of the Firm. So basically we have operations, which is mostly concerned with efficiency, dealing with the first order network, and the second order network, which is more dealing with effectiveness through sort of a stateful view of the world, looks at or makes use of the second order network. So the take-homes from this. Our first order internet is all about efficient production. It coordinates complex behaviors. It smooths the transition between sequences of action. It makes things easy, behaves like a cerebellum. Our second order network should then do all the things about deciding what needs to be done. It needs to maintain internal representations of the environment. It needs to construct and associate among concepts, which is, by some people's definition, thinking. And basically, it's there to do the right thing. And I'm speaking here in evolutionary terms. It needs to survive. but certainly there's room potentially for ethics to start creeping in here too. So. And so in conclusion, rather than describing the old internet as broken, I think it's more accurate to say it's just not up to the whole job. However, it is the only tool we have right now that operates at the scale that we find ourselves in and needed to operate in. And to paraphrase one last quote, we don't need a bigger boat. We actually don't even need a different boat. What I think we need to do is compose new functionality appropriate for this scale that we find ourselves in, using as much as we can of what we already have. And in short, we need to evolve. So what might this new functionality be? Well, looking at brains again. If humans have demonstrated anything, it's that having a shareable, semi-stable internal representation of the world on which to base decisions and judge outcomes, they've shown that this is an evolutionary advantage. And feed-forward circuits can't provide that. You need feedback to be able to enable that kind of control. The cerebellum by itself isn't good enough. Operations isn't good enough. An OSI-A by itself isn't good enough. We need a cerebrum, we need management, and we need OSI-B. And thank you very much.
Questions? Okay, I'll start us off with a question. How do we develop OSIB? You presented the vision of like, we need the next layer. How do we get there, do you think?
I think the hard part is this whole idea of how do we transmit concepts? So what is the internal representation of one organization? The internal sort of representations from one organization, how can they be mapped to another? And I think that's going to be an important role of this sort of this second layer of communication network. And as I said, sort of we've got a very rudimentary model of that, just looking at, say, one document and the morph, the changes that can happen to one document. One of the stories that one of the folks at Block Science likes to talk about is the ship of Theseus. It sails around the world, its crew constantly changing its parts, but it remains the ship of Theseus. Greek story a long time ago. But at some point, how much change has to occur before you have a new object? So it's this more abstract view of data, this concept that has some stability to it. How can we produce something like that?
Any more questions?
I would just like to hear a bit more about the content addressable transformers, the CAT system, where it stands related to the new model, and I think I understood all of this. I need to read it and digest it for a bit, but the non-internet protocol-based use of this, so through other kind of physical transports, be it, radio or decentralized, long-range Wi-Fi networks and things like that. It feels like that's what you're talking about, but in say, the 5-year period, I have some potential applications for both of these things, trustworthy decentralized computing and non-internet protocol use cases, so I'm trying to figure out where this stands.
That is one of the places where CATS fits. One thing to think about is that... Sorry, microphone? Sorry. That is one of the places where CATS fits, is integrating across different networks of different composition, different scales even. So what do I mean by that? The physical transport seems to be best handled by the network that we currently have. But as has been pointed out several times, there are sort of temporal differences. There are sort of, what would I say, frequency differences, delays that occur in some transactions that can disrupt communication protocols that expect sort of synchronous flows of information. That sort of ability to handle interrupted traffic may be best handled by network computers rather than the lower level. But getting back to CATS, one of the things we want to do with CATS is to integrate sort of Web 2 workflows with Web 3 workflows. So put a sort of standard protocol framework around creating a call into what data do I want processed, what do I want it processed by, and then how do I represent the result, doing all of that to sort of basic transformer functions and still maintain provenance well enough so that I can piece these individual transforms together into a pipeline. Part of that pipeline can exist on Web 2 architectures, part of it can exist on Web 3, part of it can exist on things that we haven't thought about. That make sense?
Cool stuff. Yeah, thanks.
Any final questions?
Hello. So block science, as far as I know, basically they're specializing in complexity science. And with relation to that, so complexity science is basically trying to operate in this tension between top-down engineering and kind of bottom-up self-organizational stuff. So how would you comment your proposal for this the next layer for networking computers, or network of network computers in this context?
That I think sort of our work on CATS also informs that. There are, we can be philosophical, top-down, about what needs to be done. But at the end of the day, somebody has to build some artifact that actually does the work. And if you look at what a CAT is, this transformer, this thing that does a job on some input and produces an output, it's actually a nice test platform for what needs to be added in order to make the development of these pipelines easy. So for instance, we started CATS prior to Bacalhau, integrating in with IPFS networks. We essentially had to do everything ourselves. Our current project is to integrate Bacalhau into what we have. And the design part of that shows immediately how much simpler the world is with Bacalhau existing as our interface into IPFS. And as we go up that sort of that layered network architecture, CATS, when all is said and done, should be a application layer phenomenon.
Right. Thank you very much, David.